Perfect. Hello, everyone. Welcome to another workshop series of the Hack AVS Hackathon. This one is with Drosera. We've covered a few networks before this. We've covered a few bounties before this, and we have a lot more lined up. For this workshop, we had Boba. We have Boba with us, who's the CTO of Drosera. And just to give you some more context on before I hand it over to Boba, Drosera is sponsoring a bounty worth 2.5K in the Hack AVS, which is going to be about building exploit slash risk detection contracts with the trap framework that Drosera has put in place. But for this workshop, hopefully Boba can take some time today, make the dev slash building journey for you guys a lot more easier with respect to what traps are, how to build it correctly, and if there's any specifications for this current hackathon slash bounty. Welcome, Boba, and thanks for taking out the time to interact with all the devs today.
Yeah, no, it's great to be here. This is actually the first Drosera Workshop we've ever done. So, yeah, it's great to do this. I'm excited to kind of go over everything. I'll go ahead and kick us off here. Um, so,
Yeah, just also to add on, if anyone watching has any question at any point in time, feel free to add it in the chat, and we'll take it up towards the end of the workshop.
yep,
On to you. Boba.
okay, awesome. Yeah, so there's a lot to cover, a lot of good content for this workshop today. The first thing we're going to be doing is kind of like a high-level overview, going through some of these slides, really just to provide like more context to what Drosera is, kind of how it works, and just like some other things that I feel are kind of important to understand the general framework before we really dive into code. Um, I promise we will get to the code at the end here, and we'll also walk through some resources. So one of the first things to understand here is like, what is this name, Drosera? So Drosera is actually the name of a plant, is the name of a carnivorous plant, a plant that catches bugs. That is kind of like the philosophy or ethos with Drosera, right? We are creating this protocol that actually helps the ecosystem catch bugs um, in a DeFi aligned, Web3 aligned way. Okay, so you know what is Drosera at a high level, technical level? It's a security automation layer, right? And it's a layer that essentially allows for DeFi applications to create security infrastructure and then delegate that infrastructure to operators that run it 24/7, right? It's this idea that as long as you have a network connection, right, a connection to the internet, then you can create security infrastructure without actually having to host it yourself. So why would we make a security automation layer? Um, I think like one really big thing to understand is in Web 2, the cybersecurity space has these type of emergency systems of incident response, and it's like a multi-billion-dollar industry. And in Web 3, we basically have developers waking up at 3 a.m. to sign a multi-sig, and I think that generally everybody would like to change that. And so, how do we change that? We're proposing that we need to have some type of security automation layer. So obviously, security is incomplete. Um, there's lots of different issues, and honestly, I don't think that security will ever be complete. The idea behind security is that there really is no silver bullet, and there's always going to be risks. There's always going to be some new exploit, maybe a 0 day, whatever, that needs to be handled in the future due to like new innovations and just kind of an evolving space. So the point of Drosera is really to fill those holes, try to fill in the gaps where security is incomplete so that you can have like a full bulletproof vest. And I think, before I kind of get more into some of the um, architectural diagrams. I think like something that is good to keep in mind during this workshop is this thought experiment of risk debt. I think a lot of developers are familiar with the concept of tech debt. It's that idea that there's debt that builds up over time when you add a bunch of new features to your project, right? There's just like a bunch of things you eventually need to clean up eventually. Otherwise, you kind of end up with this project with spaghetti code. So this idea here with Web3 is that everybody is building on top of each other. Everybody is trying to leverage some really cool technology that does something very special for them and it's very innovative. But the more complexity that we have in the space, the more risk that is kind of created. And you have to be able to manage that complexity and manage that risk. Otherwise, it'll eventually make you pay through an exploit, a vulnerability, something. So we need to be able to be cognizant of this idea of risk debt in this space while we can continue to build off of each other's technology. Okay, so this is probably a really good slide to to understand at a high level. If you're building on Drosera, or really even trying to understand it. Um, it's really these four components that I have listed here. You can see in the middle, we have the Drosera protocol. This is actually just the set of contracts that lives on chain, right? This is the thing that has, an Ethereum smart contract address, and it has a bunch of functions that operators can hit and users can hit. But its main purpose is to actually manage these things called traps and manage operators, right? And this is getting into one of the core principles of understanding Drosera, which is traps. Traps are essentially like a framework for security infrastructure. These are the things that users or protocols are actually creating when they're delegating it out to operators to run. You can see here that these operators are running trap logic 24/7. So they're kind of doing your passive monitoring and your active monitoring when they see an incident occur. You can see here the response contract is related to when an incident occurs. It's something that a trap creator specifies to say, hey, Drosera protocol, I want this response contract with this function to be called if my trap detects an incident. So this could be like a pause function on your protocol. It could be a swap function to maybe manage your treasury. It could be a bridge function, right? It can really be any type of Solidity smart contract function that lives in the EVM. Right. So this is what we mean when we talk about incident response. Um, it's this ability to see something and then act on it as soon as possible. And Drosera basically facilitates that through traps. And that's really something that is the focus, I think, of this hackathon is the traps aspect. How do you create those? What are those? How do they work? Yeah. So like I've said before, security infrastructure as Solidity code, that's what a trap is. And it really follows this framework. It's a pretty simple interface. And it just explains this is the actual contract of the trap, and it has these two main functions, collect and is valid. Um, collect basically just allows for you to be able to grab any data from the EVM. If you're familiar with Solidity code, you'll see it has this view. This basically just means it can grab any kind of data and it can't change state, right? Um, and then is valid takes an array of previous collects. Um, so this actually means that you can have like a time series array of collects from previous blocks. Block 10, 11, 12, 13. You can have this type of time series array. So is valid does an analysis on this array of collects, and it can determine based off of this data, did my incident occur? Based off of whatever I'm looking at. Maybe I'm looking at a price feed. Maybe I'm looking to see if a pause status has been set to true, right? Um, and you can see here that is valid is using a pure modifier. So really, this just means that is valid cannot actually query data from the chain. It can only really do math and logic inside of is valid. So it's really only leveraging this array of data points. Um, and it returns a Boolean. So it's basically trying to indicate if I return true, then my trap is valid. My validation conditions haven't been broken. Everything is fine. But if it returns false, then that means my validation conditions have broken. An emergency response should be triggered. And this slide is really just to kind of like hit home on collect and is valid. Really, collect is fetching any state data. You can grab data from multiple dexes, oracles, bridges, layers, lending protocols, really anything. Um, and is valid, like I was saying, allows you to do that time series analysis. And Drosera houses all of this stuff. It's basically that protocol that holds and manages and facilitates uh, the trap framework that you as the developer are creating. I think this right here is probably one of the better diagrams we have to really understand this framework, right? Um, and I think that visually it's really great because it can show you how there's kind of like this chain of blocks over time, right? All the way up to the latest block at block 299 here. And you can see the collect function on this trap is collecting any state and it's hitting this EVM state. And then we're also waiting for future state, right? We're waiting for the new block to be mined, to be propagated before we can actually collect any data. Um, you can then see that this state is pulled into the isValid function where time series analysis is done. And previous block states are provided to this function to do that analysis. Um, and a really good additional point here is you can see this block 293 state is dropped. This is because this design with traps is very much like a light client. It's almost like a rule framework for an operator to be a light client for your security infrastructure. That operator running your trap isn't going to contain, all of EVM state, right? It's not going to be like a full archive node for the EVM. It's really trying to be a very slimmed down and recent version of the of an EVM validator. You can see here as well that if is valid is false, then we have this emergency response. Your operator is basically going to be performing that emergency response in doing consensus with the other operators running your trap. This is also a good diagram to kind of show how interconnected traps are, and really this just provides like a good example of showing that kind of web of connections. You can see here this trap contract has like the collect and is valid function, and you can see collect is connected to all these different contracts that live on chain. We have Dogcoin contract, Dex, Bridge, and there's all this different data that lives on those contracts. We're able to collect it all, and we're able to do analysis on it all through is valid. You can also see there's this group of operators that are running this trap. Um, and then they're connected to an on-chain contract. This is like part of the Drosera protocol on-chain that is then connected to an emergency function. Um, this is basically just a router to have your emergency function get called. This isn't particularly important for, this hackathon or really this workshop, but I would say that this portion right here, the showing this emergency function, is just important to understand for the context of how does Drosera work and like what is the output or the outcome of a trap triggering or identifying a risk or an incident. And so when I talk about, a user creating a trap, who is that? And I would say that the most straightforward answer here is protocols. Like, realistically, a protocol is the one that is going to want to have some type of system for doing incident response, for handling risks. So a trap creator would tend to be somebody that is, running a protocol on chain, but really, it can be anyone. It could be a single user that creates a trap. It could be a DAO that creates a trap. Really, everyone can do this. Uh, Additionally, more context. Um, how these operators are actually incentivized to run a trap. It's really as simple as on chain. People can create token streams that are distributed to operators while they're running this trap. Um, and this just makes basically a marketplace that kind of aligns with Web3 ideals and the ethos of Web3, so that you can have this open marketplace where anybody can seed value for somebody to perform some type of task. Um, this is some nice insight into how all this stuff is possible. Um, this is like, a very unique use case, I would say, for smart contracts, and it's kind of an interesting use case for just security in general. How is this possible? Really, it's possible through advancements in ZK, and a lot of just advancements over the past year and a half, to be honest. Um, Essentially, the best way to understand how this stuff works is that Drosera is leveraging the EVM as a data availability layer. That data availability layer is like your collect function. It's how you're grabbing data. You're grabbing data objectively from this function and this function, from many different smart contracts. And then the ZK portion is for objective historical analysis. That's your is valid function, right? It takes an array of all this different historical data that you've actually collected, and you can objectively say what the outcome of is valid is. It's like proof of execution between the collect function and the is valid function, right? Um, these are really just kind of talking about some of the values of having decentralized EVM security. Really, it's quite simple. We just want to create something where a system where anybody, anywhere can be a participant. Um, there's no special hardware you have to have. It's a decentralized system. All you have to have is like an open network connection and be able to specify your security conditions. It's built with smart contracts, right? So it's an EVM native security infrastructure solution. Um, and because it's an open source framework, really fully leveraging the EVM and Solidity, it's actually a way for us to foster a community between Solidity developers and security professionals. And we'll actually, eventually here go over some resources that are shows that some of these communities are already forming. Um, and so Drosera can act as like a strong boost to those. Lastly, here on some of the benefits and just attributes of EVM native security. Um, Composability is pretty obvious given that smart contracts are really how Ethereum has been built to what it is today. People are building contracts on top of contracts, and with Drosera, since it's all contracts, it is very composable. In terms of extensibility, because we're using ZK, we can add a whole host of new functions, right? We can add many new functions to traps, and we could actually even add new opcodes. Um, I think the third bullet point here on community is actually the most important. Um, I think that security projects have actually had some trouble trying to kind of garner a community, but I think given that the solution is like very transparent, open source, really allowing Solidity developers to leverage the system using skills they already have, it's actually going to be a really great solution for people to form around and say, hey, look at this library I made, or look at this trap that I made, and kind of share in the development process. And lastly, um, because this is security infrastructure as Solidity code, it's actually incredibly testable. Like you can actually just use Forge, Foundry, Anvil to test your security infrastructure natively against your protocol, rather than trying to spin up like a Node.js server and like run a bunch of database stuff. You can just run a trap. Okay, so I touched on quite a lot there. Um, for high levels, like, what is a trap? High level architecture. Um, Now I'm gonna kind of like just look at some resources that are available. These top three, I'm not gonna go over. Obviously, it's just like the dev docs, um, and our example repo that shows some example traps, and then a template that shows like how do you actually have a trap in Foundry, and how do you test it. If you're making a trap for this hackathon, those should be things that you should look at because that's probably the most helpful to understand how do you develop this stuff. But these last two are incredibly helpful. The DeFi Rec database and the DeFi Hack Labs repo. I'm going to walk through those two because I think that not many people are familiar with these resources, and they should definitely take a look. So let's just like look through these. So the DeFi Rec database, obviously this is kind of crazy. It's showing like almost $80 billion of cumulative loss from exploits. It's truly crazy. Um, but this is actually where this database shines, is that they actually have just like a repo of all of the different exploits that have occurred. Uh, and so if you filter on date here, you can see some of the most recent hacks and exploits in the space. And this is a really great resource for if you're trying to create a trap, because you can actually just go see what are some examples of exploits that have already occurred, right? So even just this first one um, that was just, a couple days ago um, was an access control exploit. And if you look at the details, it tells you like what was the involved contract addresses, details of the exploit. It gives you attacker addresses, transactions. It gives you tons of really good data. So if you want to simulate an exploit to show how a trap could be helpful, this is a really great resource. And it touches on things from like Polygon, Binance, Optimism, Arbitrum, Blast, really the whole 9 yards. Um, yeah, so this is really great. Secondly, DeFi Hack Labs. This is also a super great resource if you haven't seen it before. Uh, Basically, it's very similar to the previous resource in that it's showing different exploits and hacks that have occurred. But for this one, they actually show this list of past DeFi incidents where you can actually see tests they created with Solidity. So you can see they actually have a Forge test here that you can actually run locally. And if you look at the contract, you can see that they have basically just like a simulation of actually performing the exploit, um, and doing it in a forked environment. So they actually fork mainnet at a particular block, and then they can simulate the hack that occurred. This is like very, very strong for us because if we're creating a trap, we can just literally leverage this code to simulate the exploit and run a trap inside of this test environment and see that the trap actually detected the exploit, and see what type of emergency action that we could have taken. Um, so yeah, this is also great because they have tons and tons of resources here. um, I think, what do they say? They have over, yeah, like 400 examples. So if you're trying to find a real world exploit to try and simulate, then this is a really, really good resource. Okay. Additionally, like if you want some more reading material on traps on Drosera, then we have a bunch of different articles and videos that we've created. If you go to uh, our account on X, you'll see we have this WTF is a trap, the inverse finance attack video, where we actually walk through a trap example of um, basically a trap that can detect an exploit that was done on inverse finance. And lastly, we have another article that talks about how you can bring very unique information on chain, consensus layer data on chain, and how a trap could actually leverage that. Um, you could think of that as like a trap being able to see if a validator got slashed or if they missed an attestation. Um, this is something that really wasn't possible before, but with traps plus new technology being created by P2P and open layer, bringing this data on chain, traps can leverage it to take emergency actions. Okay, so hopefully I am making a good time. I think I am. Um, Now we are going to kind of like go into the code portion, where we're going to walk through our development environment and look at a few scenarios that I put together. Um, we're going to look at two different ways of doing development: local development and chain fork development with traps. That's just really like running forge tests with traps. And what is the difference between running tests in a forked environment where you're actually forking mainnet, and then an environment where you're actually just doing everything as a simulation, running your own node, your own forge test without any forking. So we're going to talk about these two scenarios: token risks, bridge risks, um, as well as some advanced examples we'll get to at the end for the Olympus DAO exploit and the Nomad exploit, where we're actually just going to fork mainnet and then look at the exploit occurring and see a trap that can detect it and take an emergency action. So let's look at that. Um, these examples that we have is from that examples repo that I was talking about earlier. I have a branch called DoraHacks Workshop that has some of these new examples in here. Um, and so I basically created these three folders that are like fairly new. One is for bridges, the Nomad hack. Another one is for the Olympus DAO hack under tokens, and a sandbox. The sandbox is really just for me to talk about development, local development, for development. Um, so I'm actually going to start out talking about fork development. So I have this fork trap here under traps in the sandbox. Um, and you can see that it's relatively straightforward. It follows the same type of format as the interface I was talking about earlier, the basic trap interface, where we have a collect function and an isValid function. You can see that this collect function is calling this other function called isBridgePaused, get some uni data and get some unipool data. And then we're passing all the information that we've collected into this like custom struct that gets returned from collect. The actual functions themselves are just defined below. This is the address right here of the actual Uniswap token that lives on ETH mainnet. This is the actual USDC WETH pool that lives on mainnet. And then this is the Synapse Bridge address. And I can call all of these different functions from the contracts that live out there based off of these interfaces, right? If you just go to Etherscan, you can go and find all of these different functions, right? So for Synapse Bridge, there's this this address right here. Let's just like go find it. So if I go to Etherscan, I can put in this address for the Synapse Bridge. You can see it has this little tag here, a public name tag. You can see that that's the Synapse Bridge. If I click on contract, I can go to read as proxy and scroll down here. You can see all these different functions that are queryable, and one of them is paused, right? You can see it's false. Obviously, Synapse Bridge currently is not paused. But this is one of those functions that I was just able to query in our trap, right? And so you can do this for pretty much all of these addresses, right? If you're familiar with Solidity development, this should be very, very familiar to you. Okay. And then also on this fork trap, you can see it has the isValid function, right? It takes an array of these custom collect structs that come from collect. And our conditions are really simple. Basically, if the length of the data we received is 2 and the Synapse Bridge is not paused and the latest uni amount data is greater than the previous uni amount data, then return false. It's just kind of like a condition that I threw together. This is kind of the beauty of traps and Solidity, is that all this is programmatic. Like, you can make any conditions that you want, however you see fit. A risk to you as a protocol may be not a risk for another protocol, and so you want to have programmatic control over what you determine should be considered valid and what is considered an incident to you. So this is just the basic trap, right? Let's look at the test, us actually testing this against mainnet. So you can see in this test folder, we have fork trap T, and the test is like super simple. When you're doing fork testing, you'll see this is a kind of a common pattern. We actually call vm.create select fork, and then we specify mainnet and then a block number. And we kind of want to specify these two different forks because we want to be able to select them inside of our test. So you can see below in our actual test, we say select fork, and we select this first one, right? When we select that fork, we're like kind of like shifting our test to the state that exists on chain at that block. And I go ahead and I can deploy our trap, this fork trap that we created, and I can call collect. And when I call collect, data will get this custom collect struct of data, right? And so that's actually going to grab these functions, right? It's going to grab the pause status and some of this uni data, and it's going to get returned, but it's going to be specific to this block number. And so we can collect that data and then put it in this array. And then I can actually select uh, the next fork, right? I can select this other block number, and then I can run collect again. And you'll see that actually gives us different data, right? Because we're actually at a different block number historically. Um, Once we've collected all of this data, we can pass it into the isValid function where it will run this analysis, right? This isValid analysis off of this data. So I can go ahead and run this really quick. I believe this is in the sandbox, so let's just go look. Yep. Okay. And so I added, high verbosity. That's this dash VVVV to show you, well, first of all, it passes. So our expectation that our validation conditions were set up to trigger was correct. It did trigger that is valid to false. And we can actually look at all of the data. You can see right here, this is when we select that first fork, right? Um, and you can see all this different data that we grabbed. The pause function, it's right here, and the result of the pause is false, right? And then we get some uni data, which is just a balance. You can see this balance, and you can see liquidity from get some uni pool data, and we're able to get that as well. Um, and so we can see why this triggered as false was because if we look at is valid, is bridge paused has to be false in order for this to trigger, and then uni amount of 1 has to be greater than uni amount of the 0 index. And so that is actually going to be this guy right here. These two numbers, this 756 and 818 number. 818 is greater than 756, so this passes. We return false, right? And then you can even see when the isValid takes all that data in, you can see all of it being passed in here. It returned false, which is what we expect. Um, so this is like a very simple example of like a trap that's actually forking mainnet. Um, let's go ahead and look at something that's like maybe a little bit more complex. We have a local trap. And a local trap is basically an example that I made to talk about how you test, traps locally without doing any forking. So perhaps let's just look at the test here. And if we look at this test, what I did here was I'm actually going to do like a little mock bridge. I made a little mock bridge protocol, and then I made my own protocol. Um, and I set them up by just deploying all of this information or all of these contracts, mock bridge, my protocol, my own token, um, and then my protocol is unique. It's basically just a very simple protocol where I have these functions where I can just add tokens to it, and I can add bridges to it, and I can get the tokens and the bridges. It's just a protocol that keeps track of bridges and tokens. That's it. And so in my test, you can see that I added this mock bridge, I added these tokens, and then I added the mock bridges receipt token. Um, and we can look at that mock bridge. And you can see it's just like it's a mock of something that tries to do bridging. So it takes in tokens that were sent to it from a user, and then it mints a receipt token to that user so that they can redeem later. This is kind of a very simple bridge pattern of like mint and burn um, in order to get you from one ecosystem to the next. Um, and so what this test is actually trying to do, and this trap, what it's actually looking for, is it's actually checking to see if there's a mint and burn issue, right? If there's ever an issue where the bridge is like minting tokens out of control, um, and the amount locked doesn't match the amount um, minted. And you can see this little for loop here is going through all of the bridges, um, and then all of the tokens. It's looking at the locked amounts in the bridge, and it's checking the total supply of receipt tokens. And it's just making sure that it adds up. If it doesn't add up, then it's saying there is some type of mint and burn issue, right? Collect will return all of that data, and then is valid will actually um, look to see if there was ever a mint and burn issue flagged. And if it was flagged, we're going to return false, right? So trap is basically just seeing, is this bridge getting exploited, right? Um, and you as a protocol, it may make sense for you to monitor your dependencies. So you might want to monitor your bridge to see if it ever gets exploited, right? Because you don't necessarily want your protocol to be using an exploited bridge, because that can have, bad effects for users and your protocol in general. So we can look at the test we have here, and what we're doing is we're just doing what we did before. We run collect, right? And in this case, I'm just passing a single piece of data into isValid to see if an exploit was seen. And you can see here I'm saying assert. I'm asserting that no exploit should be seen. And then I actually use this to roll to the next block. For forked environments, you saw earlier that we used a VM create select fork, and then we selected the fork. But with local environments, you're not going to have that. You're just going to have the ability to kind of simulate rolling a block number forward and then changing the timestamp, right? So we roll the block forward one block, and then we also roll our timestamp forward 12 seconds, right? Because in Ethereum, at least ETH mainnet, each block is going to be 12 seconds. So this just simulates moving the progression of time. And when we get to this next block, we're actually going to perform the exploit ourselves, right? So with this ERC20 mock that lives on the bridge, I'm going to go ahead and I'm going to mint, 10 Ether worth of this token. And then I run the trap again in the next block, and you can see that we're asserting that our validation conditions were broken and the exploit was seen, right? This token got minted and it doesn't match locks in the bridge. And then you can see that as an emergency response, we go ahead and we remove the bridge from our protocol in order to protect our users. So I can go ahead and I can run this test. And this is in Sandbox. Yeah, you can see it passes. And if we want to see like more verbose, then you can see all this different data that we were checking for. It doesn't just show you like, the rules and warps, but it shows you is valid, right? At the beginning, where there was no exploit occurring, you can see the local trap ran as valid and saying it's true, right? It didn't see any issues with total supply or like a mint issue at all. But then later, after this roll and warp, you can see that we compare our total supply, and you can see this burn issue shows up true. And so the result of is valid is false. And so we go ahead and we remove that bridge, right? So this is another good example for just kind of some simulation of trap experimentation. Okay. So I think lastly, what I'm going to show you guys is the more advanced example. I won't walk through all of it because it is like a bit more advanced, but it is pretty cool just to see. Um, so the first one we're going to look at is going to be the Olympus DAO hack. So let's go there and let's look at just the test here. You can see this test is like much more involved, right? We've got all these different addresses, protocol bytecode paths, and it's pretty wild. But let me go ahead and try to break it down for you guys. Of at least what are the important things to understand about, you know, actually simulating against a real exploit. Um, you can see the first thing here is that we actually created a fork. So we were creating a fork before the exploit actually occurred on mainnet. And what we're doing is we're actually going to go ahead and use this really cool function that Forge provides to us called vm.etch. Um, Etch basically allows for us to replace or override in our fork the bytecode of the Olympus DAO contract, basically. And this is really important for us because we can actually like add new functions. So we can add like pause functions into this contract and show that when we add this pause function and then we actually hit it, when we try to perform the exploit afterwards, it fails. And that's like really important to show, exploit mitigation, etc. Okay. And you can see that we basically like doing what we did in the previous tests, right? We do collection of data, and then we roll through multiple blocks. We do more collection of data, and we actually perform a hack in here. And so what I'm going to do is just show you guys the result and what actually gets shown in the terminal here from running this test. Oops. And so I logged some of this so that it was just like more human readable. You can see we started this block. We collected data from this block. The bond contract ohm balance was this 30,000 number. And the attacker's ohm balance is 0. We warp 10 blocks ahead. The attacker performs the exploit. The bond contract ohm balance after the first hack, it actually gets like cut in half, right? So now it's only 15,000, and the attacker's own balance is it got basically the difference, right? They are able to siphon this out of the contract. And then we go ahead and we have Drosera collect data from that block and then perform the trap logic, right? This validation logic. And Drosera identifies the state as invalid and emergency response is required. At the next block, the attacker attempts to perform an exploit again, but the transaction reverts because the contract is paused now. And then you can see that they weren't able to get the rest of the tokens out of this contract. So this example is really cool. If you guys want to go look at this DoraHacks workshop branch on our trap examples repo in our GitHub, you can like read through all of this, and it should provide some really good insight. Lastly, we're just going to look at the Nomad hack in this bridge folder. So let's just check that out. This is also like I would say a fairly advanced example. You can see that we're doing, very similar things to what we've done before. Selecting a fork, creating these different forked environments where there's like a pre-exploit fork and then a post-exploit fork, so that we can grab data before it happened and then grab data when it happened to identify, look, this exploit occurred. Um, and I'll just go ahead and run this guy so you can see the kind of human readable logs. Okay, so yeah, for this one, this was basically an exploit where, like I was saying here, attacker can copy the original user's transaction call data and it can replace the receiving address with a personal one. So this attacker was actually able to hit multiple pools, but we're just going to focus on how he could have mitigated damage in regards to the wrapped BTC pool. You can see that we collected data at this block number. We warped to the next block, and we can see that hacker performs multiple exploits. The bridge balance drops to 628 from this 1028 number. Drosera collects the data when this exploit occurs. It performs analysis on it, and it identifies, yes, this dropped by almost, like, I think it was 30% or something like that. That's what the trap is set up to do. It's supposed to look for if there was a 20% drop over a single block, then this is like a huge problem, or a 30% drop. And so Drosera submits a claim, the state's invalid. The attacker attempts to perform the exploit again, but the attacker's transaction reverts because the Nomad contract is paused from Drosera performing the emergency response. You can see the bridge balance didn't change, and in turn is saved about like 42 million in wrap BTC. Additionally, there actually is a lot more that technically would have been saved from this, because technically after this block happened on chain, there were many follow-on transactions trying to siphon other tokens out of other vaults. I think it was like USDC maybe, or some other stable coins. So that is really everything for yeah, all of these different examples showing how you can actually uh, perform trap detection and incident response on real world exploits, as well as like some some mocked exploits. Um, do we have any questions or anything like that?
Seems like we're good for now.
Okay.
But we will also drop the Discord link in the chat in case anyone has any questions and want to catch up later.
Yeah. I would say that is like essentially um, kind of like everything that we kind of have here to go over in this workshop. Hopefully this is all like really helpful for anybody trying to work on traps for this hackathon, or anybody maybe watching this later after the hackathon that is trying to understand trap development. Hit us up on Discord, uh, DM us on X, and we'd be happy to collab or work through anything.
Absolutely. Thanks for that, Boba. And yeah, like Boba mentioned, if you want to revisit anything, if you want to just go through any section in particular, again, feel free to rewatch the live stream. All the workshops would be linked on the workshop tab of the hackathon page. But for this one, this was it. Thank you so much, and feel free to join the Discord in order to also connect with other developers who you could build with. Or if you have any question regarding the submission, feel free to hit me up on Telegram. I am at Mishika MISHIKA 251 on Twitter or Telegram. Happy to assist you in anything. And yeah, that was it. Thank you so much for the time, Boba. Really appreciate it.
Yeah, this is awesome. Thank you for everything. All
Thanks
right.
for watching, guys. All the best.